Alright, let's go through some trig proofs. So, these are four kind of more challenging trig proofs. They're going to be using a little bit of knowledge of quadratics, a little bit of knowledge of perfect squares, and a little bit of knowledge of the completing the square. So, immediately, I hope you notice that we've got the difference of two squares. So the left-hand side can be written as tan theta minus sine theta times tan theta plus sine theta. A really nice method of manipulating a quadratic to turn a subtraction problem into a multiplicative one. What was then quite interesting is the next step I took, because I think there's an easy way to do it, but I'm just not too sure how. So I wrote this all out as sine theta over cosine theta plus sine theta. So I'm just using the identity sine over cosine as tan. Sine theta over cosine theta plus sine theta. And then what I did, I saw that I need a high power of sine, right? I need sine to the 4. And so I factorized out sine from both the brackets. So I pulled a sine theta out of this one, put it out the front, and I pulled one out the front of this one. So that gives me 2 out the front, or sine squared out the front. What's left on the inside is 1 over cosine theta plus 1. 1 over cosine theta. Oh, sorry, that's meant to be the... Sorry, that was a minus, wasn't it? Minus, and this one was plus. Plus 1. So I have sine squared theta 1 over cosine minus 1 times 1 over cosine plus 1. Difference of two squares has now been manipulated down to having this. So 1 over cosine is sec, so that's sec theta minus 1, sec theta plus 1. And I just went backwards. I went back to expanding this thing. So I went sine squared theta, and now I've got sec squared theta minus 1, which I believe is an identity. So that's sine squared theta tan squared theta. But how do I get, I should write this neater, how do I get sine to the 4? Well, that's just sine squared theta over cosine squared theta. I'm going to do this in one step. Hopefully that's still in the frame. One step is sine to the 4. And I'll be left with 1 over cosine. And that's the end of my proof. Or the proof. It's not really mine. There's probably a simpler way to do it. If you can notice anything, just let me know. I'd be more than eager to see a quicker and easier solution to that one. The second one, hopefully it's in the frame. I've got brackets, and I don't really want those brackets there. So I think the best thing for me to do is to expand. So left-hand side is sec squared theta plus 2 tan theta sec theta plus tan squared theta. So I just don't like the brackets, so I wanted to get rid of those. Now expanding was quite helpful. Now I wrote these all over cosine, so that's 1 over cosine squared theta plus 2 times sine theta over cosine theta times 1 over cosine theta plus sine squared theta over cosine squared theta. And notice that I've got a cosine squared at the bottom of everything. So let's bring that out. 1 over cosine squared. What's left on the inside is 1 plus 2 sine theta plus sine squared theta. And that looks a lot to me like a quadratic. A squared, A constant. So let's factorize it like it is a quadratic. 1 plus sine theta squared. It's a perfect square, isn't it? It's all positive. We've got 2 of the variable in the middle and the variable squared in the end. Now I'm just going to use an identity for cosine squared. So on the top I'm going to get 1 plus sine theta squared, so it's 1 plus sine theta times 1 plus sine theta. But on the bottom is, well, cosine squared is 1 minus sine squared theta, isn't it? From identities. And so what's on the bottom is actually 1 plus sine theta on top, 1 plus sine theta on top. But on the bottom I've got difference of two squares again. So I've actually got 1 plus sine theta, 1 minus sine theta. And look at that, those cancel out. I've got 1 plus sine theta on top, 1 minus sine theta on the bottom. That is the right hand side. End of proof. That is a really nice problem. I liked how there was quite a bit of little reflections of quadratics in there. Really quite cool. Okay. This third one is pretty gnarly, namely because it's got an A and a B in here. So it's not just one variable all the way through. So if I was doing this, there's a little trick that makes it nice and easy. The left-hand side, I'm going to write this as cosine squared A over the whole bottom. Take away cosine squared B and over the entire, I would say bottom, but I need to be a bit more of a mathematician, over the entire denominator, over that whole denominator function. And notice why I've done this. Cosine squared cancels, cosine squared cancels. Now I'm just going to go straight into writing this as sec squared B minus sec squared A. Because 1 over cosine is secant, and so it's squared. So we've got secant squared B minus secant squared A. I'm just wondering, I've done this a different way before, but I'm wondering if that could be a difference of two squares. Don't think that's actually going to help us in this case. What I did was I wrote this as that's tan squared B plus 1 minus tan squared A plus 1. When you do that full subtraction, you get tan squared B minus tan squared A, and that is the right hand side end of proof, because the ones would cancel there. Tan squared minus tan squared, 1 minus 1, it's gone, and we're done with that proof. It's actually probably the easiest one on here once you understand to split that that quotient function up into those two. Last one for today. Hopefully you're seeing a wee bit of a pattern with these ones. There's another difference of two squares. So this left hand side, it's not immediately obvious it's a difference of two squares, but that's sec squared, isn't it? So that could be written as sec squared theta minus 1, sec squared theta plus 1. That's how I'm going to do that. Well, sec squared theta minus 1 is tan squared. So it's tan squared theta. Then we have sec squared theta plus 1, and it still remains in that bracket. Now, a little trick here. I'm going to replace sec squared theta. And I'm going to do that because I need to get a really high power of tan, and I've only got tan squared at the moment. So this has to be written in tan, doesn't it? There's no way I'm going to get a high power without replacing this. So that could be tan squared theta, and sec squared theta, well, that's tan squared theta plus 1, but I've still got that plus 1 there. And look, that's probably where that 2 is going to go. So I've got tan squared theta plus 2. And watch what happens when I expand this. Tan to the 4, 2 tan squared equals the right hand side, doesn't it? I know it's not written perfectly, but the addition is, there's a word for that working both ways. Can't remember what it is. And that is the end of proof. So tan to the 4 plus 2 tan squared theta from expanding that. Awesome. Those are really nice proofs. Let me know how you get on, and maybe let me know if there's some shortcuts to that using maybe some better identity usage.